Okay, welcome back. This is Dr. Reveles, and now I'm going to show you how to solve this problem of evaporation using linearization on Excel. This is the problem. The amount of water evaporated from a surface can be approximated by the numerical relation. Here is given the numerical relation, where GH is the mass rate of evaporated water. A is the surface area of water. Phi is empirical constant, and XS is the mass fraction of saturated air, and X is the mass fraction water in air. Okay, first thing you want to look is what are the variables? Out of all these equations, the variable is X, which is the mass fraction water in air. And that's going to be affecting the mass rate of evaporated water. So these are the two variables, GH and X. All the others are constants. MAPE, or mean absolute percent error, may be defined by this equation, where you take the difference between the actual value, this is the actual value, AT, and the calculated value, and you add the errors. Okay, this is the problem. Given the data below, linearize the equation to determine the saturation fraction and empirical constant phi. Right? So you are going to linearize this equation. So that's what we're going to do here. This is the starting equation. We can FOIL this equation. And then by FOILing, you distribute this. And now you, again, keep in mind that the only variable is X. All the others are constants. And now this already has a linear form. You just change this again. This will be Y, which is the independent variable, equals these two constants times X plus these three constants. So that's what we need for the linearization. Your Y, or your independent variable, is GH. Your X is this mass fraction of water in air. The slope is this, the product of these two constants. And the Y-intercept is the product of these three constants. Okay, so we're ready to make the graph. So we're going to make a graph here from your X and Y. See, this is your X and this is your Y. So I'm going to here insert chart, scatter chart here. And just to be sure that we have the correct variables. Let's see, select data. Okay. Let's remove this one, remove this one. Okay, this is your Y. This is the model. And this is, of course, they depend on the X variable. And this is the Y. Okay, actually you only need one. This is not needed. This is your model. This is your model with this linearized equation. So okay, let's have, once you have this, let me just copy here. How your equation looks. Of course, you insert the equation. Remember, you click, I just added these labels. But when you hit right click here in format trend line, that's where you can add this linear fitting, display equation, and then the R square. Right? Okay, now you have the equation of your solving the problem. Remember, the slope is minus A phi. So I'm going to copy here, the slope is negative 2946. And the Y-intercept in this problem is phi 20. So copy this equation. Now I can calculate from the model. Remember this, the model is the dashed line and your experiment are the dots. So let's calculate with the model what is the rate of evaporation. So I'm going to copy here using this formula. This equals, let's see, the slope times X plus the Y-intercept. Wait, the Y-intercept is actually this. Y-intercept, I need to copy here. So okay, that's the Y-intercept. And then because the slope doesn't change, I'm going to keep that constant, and the Y-intercept also doesn't change. I'm going to keep that constant. Okay, and then I'm going to calculate with this formula. Again, remember this column is the experimental, are these circles, blue circles, and these other columns is your model. You see, this is the Now we have the model. We can now calculate the error or the difference between these using this formula. So it will be equals absolute difference of these two numbers divided by the actual number, which is C23. Let me see. Okay, that's the difference between the two, the model and the experimental over the actual number. That's correct. So the actual number is this column. Yeah, let me fix that. The actual number is B23. The experiment. Let's see. Experiment. Okay, that's the difference. Take that difference here, and we can calculate your okay. I'm using this formula, right? So this is the absolute difference between these two divided by the experimental. This is how far is the model from the experiment. Added all of them. My formula is add all of them, divide by 100, and multiply by 100, divide by the number of points, which are 8 points here. Okay, finally, because we know the slope is here. Slope equals minus area times phi, and area is given. Area is this given, so we can calculate phi. Right? Phi equals the slope divided by the area. Okay, I'm just going to add a minus here because it's minus. Okay, that's the, and finally xs. Okay, xs is your y-intercept is a times phi times xs. This is your y-intercept. So xs is the y-intercept divided by a times phi. That's what we have done. Explanation. Let's see what the explanation will be. We can rearrange the equation, plotting. Let's copy here the explanation. One can rearrange the equation into a linear fit. Remember, the important thing for now is that I identify what are your variables. Let's read the explanation. One can easily rearrange the equation to a linear form, plotting the data and getting a line of best fit given us values for the empirical constants. It's empirical constant and saturation fraction, right? This is the empirical constant and saturation fraction. From here, we can use our values for the slope and y-intercept to calculate forecast values. Remember, these are our model. At each mass fraction, in calculating this, we can now estimate the our mean absolute percent error. Okay. So look at this problem. Again, it's not exactly the same as the one you have in your workbook, but definitely you can use this as a guide to how to solve the problem in your workbook. Okay, thank you and have a good day.